morning, guys. I'm Gatti Victor Pirish, civil engineering student level from the Faculty of Engineering, the University of Korea. Today we're going to talk about structural analysis. If you remember, in our last video, we talked about stable structure, determinate structure, and redefine the concept of stable and unstable structure. So today we are going to start with analyzing of structure like beam. But before starting the analyzing of the beam, we will first of all put more emphasis on the sign conventional using structural analysis. Okay, first of all, we have to know that the structural analysis due to the load that is applied on the structure. So actually, if you have, for example, a beam, let's say a uniform distributed load, let's say a uniform load. Let's take a simple supported beam. On this beam, we apply a certain load P. The load that we are applying on this beam actually will cause a certain number of stress internal to the beam itself. So we will have the bending moment as internal reaction of the beam. We will have the shear force and we have also the deflection. But to find the bending moment and the shear force that will be in our next video, we are going to learn how to use the sign conventional. That's because in structural analysis we have the positive and the negative, but for the course of our video will be more focused with the positive conventional sign. That's, for example, in the case of the moment, if you take now the case of the uniform distributed load on the simple supported beam, with the uniform distributed load. Yeah, actually, if you are to represent the moment actually in the positive conventional sign, that's how we are going to represent for the moment. The moment actually about the reference axial we call theta. So this is the positive conventional sign for the moment, and for the shear force actually we have this as our positive conventional side. This the right and this the left. And to find the shear force on the structure or the bending moment actually, you know that we have to first of all make a cut. But before making a cut, first of all we have to start by the free body diagram. So we start a simple analysis of a uniform distributed load of a simple supported beam, so that we can present the conventional sign for you to see how we are going to apply it when analyzing the structure. So if we still have our uniform distributed load on our beam actually, to see the bending moment and the shear force that are internal reaction to our structure, that is this beam actually, we have to make a section. But before making a section, we have to make the free body diagram. The first step is to make the free body diagram. That's how do we make the free body diagram? We make the free body diagram by removing all the support and substitute the support by reaction forces. So we remove the support on this our single supported beam uniformly distributed, and we represent the support by the reaction forces. So that's what it's going to give. After removing the hinge support that we have on this axis, we know, as on the first video we talk about the type of support. We talk about hinge support, we talk about roller support, we talk about fixed support. Actually, to have a stable structure, because this structure is stable, as in the previous video we mentioned what is a stable structure. To have a stable structure, we can have a stable structure by a combination of hinge support and roller support, or a combination of hinge support and another hinge support. So after removing the support, the hinge support, actually we have, if we call it point A here and here our point B, we have at point A here we have the reaction forces along the x direction, and we have the reaction forces along the y direction. That's for point A. And for point B we have, since it's the roller support, we have the reaction forces along the y direction. As I told you previously, as in the previous video, I told you that the number of restriction is equal to the number of reaction forces. So if you remember well, you understand why actually you have the one reaction forces at the level of our roller support. So after this our free body diagram, we have still the reaction forces. Now we make the section of our structure. Let's assume that our structure, the length of our structure actually, our structure has actually the length M is the length of our B. Actually, we will make a cut in between the point A actually to a certain point X actually, and we will represent the external reaction forces. This is our reaction forces along the y-axis, and this is our reaction forces along the x-axis. So after making a cut, we have now to represent the internal reaction forces on our structure, on our beam actually. So we know that the bend moment, according to the position in the positive conventional sign, we are at the right, and make my section at the right, and I have the distance from A to a certain point X. Is our point X. So this distance we call it A. We call it directly X, and we represent our bend moment actually like this. And I will abbreviate our bending moment by BM. And for the shear force, we represent it like this, downward, looking downward because we are at right. That's the representation of our shear force, and this is the representation of our bending moment. So as you can see, when we make the section at right, I make my section, I make it cut at my right, and then I do exactly what actually I have at my right and represent it here as the bending moment and the shear force. So if I was to make my section maybe on this side at my left, I will carry exactly the left portion of the sign convention of the bending moment and the shear force to come and put it exactly like this at my left. So remember, this is the positive sign conventional for our shear force, and this is the positive sign conventional for our moment. And this is how we will represent. We'll be representing our bending moment by BM, and we'll represent by our shear force by SF. Okay, so remember, this is how we represent the shear force and the bending moment when we make our cut at the right. So if we make now a cut at our left, actually, if we make a cut at our left, actually, we will have this. How is it going to appear? That's how it's going to look like. So you have this. And don't forget, when you make your cut, when you make your cut and then you are about to represent the shear force and the bending moment, you should not forget that your external forces, that is your reaction forces, should be well represented. So it's not because you make a cut that you will remove your reaction forces. That's why we are representing again our BY forces. Remember, actually we have one reaction force because it's a ruler support. You can notice that here we make the cut at right, and then we represent normally our A reaction along the X direction and our reaction along the Y direction. So when we make now our cut at the left, we have now what? We have our reaction along the Y direction but at the B point, and then that's how our movement is going to be represented. bending moment. This is how we are going to represent our bending moment. And according to the positive conventional sign, at left we will have this as the representation of our shear force. So that's how we represent our bending moment and our shear force. But remember, this is just how we are going to represent according to where we make our section. So now for analyze, when you enter in the analyzing of a structure, normally in the simple supported beam, for example, you will have to choose, before analyzing, you will have to choose the sign, the positive sign, or the positive direction or the negative direction of your bending moment. That will be to come and add the direction. For example, if I decide that this is my positive direction, it means in this case, for example, my bending moment, if I'm analyzing, if I rho may be the summation of moment along the x-axis, this is my x-axis, this is still my distance x, this is my x. Let me say that I'm analyzing the moment along the x-axis. Then what do I have at that moment? At that moment, I'll have my bending moment that actually is opposite to the direction of my sign that I should. So I'll have a negative bending moment. In case now when I will have now to choose, I will choose instead this direction as my positive direction. If I make now if I apply now the static equilibrium equation on the moment, I will have this along the x-axis. I will have my bending moment now that will be going in the same direction as my conventional sign direction that I choose. If you people can see, you will see that my bending moment is going in this direction, and my conventional direction, my positive direction, is also going in the same direction as the bending moment. So you have in this case now positive bending moment. So you should not be confused with this sign convention and the representation of your bending moment, because this is your positive sign convention that you choose for analyze your structure. So this was all for the use of the conventional sign. You will see how to analyze a beam in our next video. If you like, you comment, you leave a post there, and then you leave your comment in the section comment. Thank you.